So hello everyone, I welcome you to the seventh session of the current problem solving session series. I am Ranamay Saha from IIT Kanpur. I am a PMR scholar at IIT Kanpur, and as you all know, this kind of sessions are meant to actually provide you some live problem solving examples. You can actually get your doubts clarified regarding the earlier assignments, questions, if any, and you can actually also try and solve live and ask your doubts about some of the uh, conceptual and problem solving questions from the current text content. So let's wait few more minutes for the students, and then we'll start our session today. Okay.
शिक्षण झालं, डिग्री मिळाली, सगळं झालं. तेच ना, हां. ते होऊन गेलं ना, सगळं होऊन गेलं आता. त्यामुळे आता तो विषय नाही काढायचा परत. तेच क्षुल्लक असतं. आमचं तेच म्हणणं आहे, की जे झालं ते झालं. आता जाऊया. आता पैशांचा विषय कशाला काढायचा? रागात का होईना नाही बोलायचं असं.
All right, so let's start first discussing the assignment questions from last week, and then we will go ahead and solve some problems on the contents taught to you in the current week. That's week 7. Okay. So starting out, the first question says, the question is about the temperature and heat generation due to plastic deformation in the various various deformation zones during machining process. We had discussed about primary and secondary zones having the maximum temperature generation because uh, anyways the flank wear zone which happens to be the zone between zone of the contact of the tool and the workpiece, that deformation can actually be controlled uh, in the pre-machining time. So major concern lies with the at the deformation zones where chip is coming in contact with the tool, and the chip is coming in contact with the workpiece, which happens to be the primary shear zone, right? So here, you know that the temperature increases in the primary and secondary deformation zone due to plastic deformation of metal in the shear zone and friction between tool and chip, respectively. So as you know, primary deformation zone faces the maximum plastic deformation and correspondingly the maximum heat generation also. So the question says the temperature or pressure or strain you have in the first, you have these options in the first blank, and then the second blank that can be about primary and secondary deformations. So if you have understood the concept of primary deformation zone and secondary deformation zone, then you can actually realize that the temperature increases in primary deformation zone uh, and secondary deformation zone due to deformation of material in the shear zone and friction between tool and chip respectively. Okay, so option A becomes your correct option here. Then going ahead, the next question says, on an average, how much percentage of heat is carried away by chips when heat transfer to the atmosphere is actually neglected? So if we have discussed that in our earlier class also, uh, the maximum heat generation happens to be in the primary shear zone. So on an average, 70% of heat is actually carried away by chips uh, when the heat transfer through atmosphere is neglected, not assumed. In most of the metal cutting operations, the majority of heat generated during the machining process is absorbed by the chip due to significant plastic deformation occurring in the primary shear zone, leading to a large portion of heat being carried away by the chip. So 70% of heat is carried away by the chips when heat transfer to atmosphere is neglected. So I hope you could have answered this question well. So the next question was a simple question, which asked which is not a joining process. You can straight away know that uh, except coating, all these processes are kind of joining processes, welding, soldering, and brazing. So the next question was about discontinuous chip formations. Okay, so the factors that contribute to discontinuous chips, if you are not aware of, are things like if the material is brittle or ductile. So brittle materials, discontinuous chips are most likely to form on machining. Brittle materials such as bronze, brass, or cast iron. Then high cutting speed can lead to formation of discontinuous chips. Okay, so low feed rates can also lead to formation of discontinuous chips. Small rake angle when the tool is in there is more friction between the tool and the workpiece. So in those kind of cases also discontinuous chips can form. Then high friction between the tool and the workpiece are related to small rake angles. So in this option, so all the three options are right. So option D answers the question. Okay. Then you had one question, which of the following is an important factor in solid phase welding? So regarding solid phase welding, there are different factors, such as some are in the during machining process, during welding process, and some are pre-welding factors which needs to be considered. Okay. So the type of bonding, specifically in diffusion bonding, is a crucial factor in solid phase welding, as it relies on the intermixing of atoms at the interface between two materials at elevated temperatures and pressure without melting the materials fully, right, to create a strong bond. So the type of bonding needs to be considered, since solid state welding is a type of joining process in which we don't reach the melting point. Okay. So the bonding in that case needs to be considered well before the welding process is done. So the next question was about the relation between rake angle and built-up edge. Uh, if you have gone through the concept of built-up edge formation, you must be knowing that the built-up edge formation are actually affected by low cutting speeds or large feed and depth of cut. Uh, it is well affected by small rake angles. So small rake angles means there is more contact between the tool and the workpiece, and there are more heat generation due to friction between the tool and the workpiece. Okay, so that equally means high tool chip friction, right? So in this case, a low rake angle can actually cause built-up edge. So I think it is clear. And then you have the question about solid-state welding process, uh, and what about the melting point in this case? So solid-state welding is a process that joins two pieces of material together at a temperature below their melting point. Okay. So generally, we reach the recrystallization temperature, and at that point, the recrystallization happens, and there are reformation of the grain structure, and which actually defines the joint after the welding process is done. The solid-state welding is a process that joins two pieces of material together at a temperature below their melting point. The materials are joined by applying pressure, which causes the atoms at the interface to diffuse and bond. So option A here is the correct option. So the next question is a numerical. We have seen extensive numericals of this kind in our earlier class. In resistance welding process, the applied voltage is 10 volts. You have to determine the rate of heat generated per unit area with 20 bridges per centimeter squared, each bridge having a radius of 0.15 millimeters. The resistivity of the material is such and such given. So how do you find that? So you know that if R with the resistivity of the material and small r with the bridge radius and n with the number of bridges. Okay, so then the heat generated per unit area is given by N by RC, right? So the number of bridges upon RC. So that RC you can determine with the relation between resistivity, okay, bridge radius and N, the number of bridges by this equation. So 0.85 R divided by pi r n. Okay. So that after plugging in the values, you will get the value of RC to be 0.000164 ohm centimeter squares, and the rate of heat generated then automatically becomes 1.219 to 10 to the 5 watt per centimeter square. Right? It's an easy formula-based question. And this was followed by a question from tool life, Taylor's tool life equation. We have done larger, very extended very extended equations based on tool life. So this type of question must have been easy for you to solve then. So in this case, the tool life of 180 minutes is given at a cutting speed of 18 meters per minute. And then it says the tool life is reduced to 45 minutes when cutting speed according to Taylor's tool life equation will be. Okay. So the tool life is reduced. You have to find out the change in speed when the exponent n is given as 0.5. Right? So it is very simple. You just have to equate the Taylor's tool life equation in both situations. If you use this equation, Vt power n being equal to constant, then and plug in the conditions parameters in both the tools in both the situations. So in one, you have a speed of 18 meters per minute, right, and a time of 180 minutes. In the second one, you have a new tool life of 45 minutes. You need to find the cutting speed when n is 0.5. Simply plugging in the values, you can find out the velocity in the second case is 72 meters per minute. Okay. So the next question is about again the arc voltage arc characteristics. Okay. The question said a direct current welding machine with a linear power source characteristics. You know by now what a linear power source characteristic means, right? So linear power source characteristics is actually yields an equation where voltage is related to open circuit voltage and short circuit current for this equation, right? Now the open circuit voltage value and the short circuit current value are given as 80 volts and 800 amperes, and it just said that during welding the machine, the measured arc current is 600 amperes. Okay, the measured arc current is 600 amperes and corresponding to an arc length of 6.5 mm, and it is 400 amperes corresponding to an arc length of 5 mm. The linear voltage arc length characteristic of the welding arc needs to be found out, right? So simply plug in the values of open circuit voltage and short circuit current to the power source characteristic, which is given V equal to V naught minus V naught upon Is multiplied by I, which is the current arc current. It is given to be 600. So just plug in the values, you will find a relation, a simplified relation where V is equal to 80 minus I by 10. Okay. Again, just if we assume the arc characteristics to be V equal to A plus BL, yeah, then just you have to plug in the corresponding V and L values, right, to find out two equations with two unknowns, A and B. So when you plug in the value of length corresponding to current 600 amperes, you find this equation, and again for length 7 mm, you plug in the value of current 400 amperes, you find this equation. Just solve these two, you'll find out the value of A and B. So you have two equations with two unknowns. So you can easily solve them to find out the value of unknowns A and B. Once you know the value of A and B, you have to just plug in the values to the initially assumed arc length characteristic. Okay, and you can find out the answer as almost around 106 minus 13L. Okay. So this pretty much actually completes your assignment questions, I guess, and uh, we will then proceed to discussing some questions out of your current text content. All right, so if you don't have any doubt, then we will actually proceed ahead to discussing some concepts out of the current week's content. So all of you know about induction welding, right? If you don't know, then induction welding actually happens in which heat generation takes place out of electric current, right? Now, uh, I think from undergraduate level, you know how an induced current is generated. Okay? So by principle, if an applied current is provided to one part, then without any contact, an induced current can be generated in a nearby part without direct contact, right? So in this case, this and then through simple kind of resistance heating, the material, the heat is generated in the material and the welding is carried out, right? So the question here, induction welding is then an example of electric welding. Okay. Now I'll ask you about something called there are names of certain in-process products such as ingots, billets, blooms, and slabs. So the first product obtained after breakdown of ingots, what is that called? It is called nothing but a billet. Let's look at some of the explanation of this kind of terms. So what actually is an ingot? Ingot is a very large casting product. It generally has a rectangular, square, and polygonal cross section in various sizes as per end use. You know, end use means or desired application. Okay. Now it has a hot top which helps in improved quality of the end product and is discarded after the production as it has all kind of impurities. Okay, it is the first product, so it has all kind of impurities, but it is very important part for good ingot quality. So sound ingots with solidification characteristics give a good quality of material in alloy steel. So now, depending upon the size and properties, we have several derivatives which come out of ingots, such as blooms, billets, and slabs. Okay? So, what is a slab? A slab is a part in which it is having a cross section, which is in which the thickness is at least twice less than the width of that of bloom. Okay? What again is a bloom? So bloom, these are rectangular or square cross sections and they are greater than 36 square inches or 230 square centimeters in length. Okay. Now blooms can be used as rolling material when manufacturing products such as seamless pipes, rails, and many more. And billets, these are usually made with the help of continuous casting machine. Okay, so we need to have cross sections which are uniform throughout the length and start from 100 onwards depending on the size of the billet caster. Okay, so by now, so you know that ingot is the first casting product, and from that we derive blooms in which the cross section is less thicker and much wider. We then call it a slab. Okay, again, what are billets? Billets are those parts which are having uniform cross sections throughout the length, and these are made with the help of continuous casting machine. Okay, so that now I think you can relate the answer to this question. The first product obtained after breakdown of ingots is called billet, right? So one more question upon this discussion is when ingots, blooms, billets, and slabs are compared based on their weight, what do you find? Yeah, so if you look at the first question, uh, we have ingots are heavier than blooms, blooms are heavier than billets. Just a second. Yeah, so ingots are heavier than blooms. Of course, ingots are the first largest casting product, so these are heavier than blooms. Blooms are derived from ingots. So blooms are then the next heavier part, and then billets are again derived from blooms. So blooms are heavier than billets, and billets again are heavier than slabs. Okay, so because in slabs we have the thickness which is almost half of that of its width. Okay, so all the three options are correct. So we have all of the above as an answer to this question. So I hope that's clear to you. If you have any doubt, you can please ask.
No, sir.
All right. So proceeding ahead, let's look into one question. Here, the question relates, you have to find out the final dimension of a block. I think if you have looked into even the initial lectures of the current week, you might be aware by now with uh, true stress, true strain, engineering stress, engineering strain concepts, then how a material yields, what are the different theories that govern material yielding, such as von Mises and Tresca theory. Then you must be aware, maybe aware with distortion energy theories. And also this, the questions we are going to discuss in this few slides are about those concepts only. So in the current question, you have the flow stress of the material is given as sigma equals 500 epsilon power zero point 0.1. Okay, so zero point 0.1 you know is the strain hardening exponent. Epsilon is the true strain, and 500 here is the yield strength. Okay, or you can say it is the strength coefficient. Now, the Young's modulus of elasticity of the material is given as 200 gigapascals, and the block of thickness 100 millimeters made of this material is compressed to 95 millimeters thickness. So the final dimension is 95 mm, and the initial thickness is 100 mm. Okay, after that the load is removed. So the final dimension of the block needs to be found out. Okay. So I've given you a few concepts here, like what a true strain is. Epsilon t, it is a natural log of original area upon instantaneous area. Or if the length part remains constant, then you can simplify this as a natural log of original thickness to instantaneous thickness. Okay. Of course, when the length is not changing. And then you have flow stress sigma f given by this yield strength k coefficient, and then a true strain upon n, which is the strain hardening exponent. So you can use these relations to find out the answer to this question. Give it a try, and then we'll see the answer in detail. Okay. All right, so I think you might have tried at least to solve this problem. Then let us see the solution. So the question says that we have to find out the final dimension when the uh, stress strain relationship is given to you. Okay. Now here the true strain, we have discussed here how to find out the true strain. It is natural log of original upon instantaneous area, okay, or you can say final area, or in other words, if the length is not changing, original thickness upon final thickness. So in this case, the length changed from 100 millimeters of initial thickness to 95 millimeters of final thickness. Okay, so using that relationship, you can find out the true strain value. And now just plug in the true strain value in the stress strain relationship which has been provided in the question. Then n has been provided as zero point 0.1, the strain hardening exponent. So you have the sigma value as almost equal to 371.5 megapascals. Okay. Now up to elastic limits, you know by now that Hooke's law holds true. Okay. So if sigma is E epsilon, okay, then E is the Young's modulus and epsilon is the uh, true strain. Now can simply replace epsilon as change in length to original length. Okay, so original length is 100 here, and change in length be delta L. You just plug in the sigma value found out just now using the stress strain relationship here, and then you can plug in the Young's modulus, which is provided to be 200 gigapascals. Once you create this, only variable remains is the change in length delta L. You can find out delta L as 0.18575 millimeters, and then that can be added to the final dimension, okay, to actually find the final dimension. Okay.
Sir,
Yeah, please tell me.
hello.
Yeah, please go
Yeah,
on.
sir. I had two doubts, sir.
Yeah.
Sir, first one was that to find the final length, I substituted ln, that true strain formula. The ln L upon L naught equal to whatever we are getting from the Young's modulus. So from that also I'm getting 95.18 mm.
Mhm.
So
Yeah, that's okay.
so
That's okay. So because this question actually deals with elastic up to elastic limit. Okay, so you can use the Hooke's law also. You can use this simple uh, this kind of equations. These are not derived anything like. So Hooke's law is an equation, but that won't hold beyond the elastic limit. So in this case, because the material is dealing within elastic limits, so if you find out the change in length using Hooke's law also, that will come equal to what we are getting through this manual formulations.
okay. And sir, one more doubt. Sir, we are getting two values here. True strain we are getting, and true flow stress also we are getting, right?
Yeah, yeah.
If we divide those two values, sir, we get some value which should be equal to the Young's modulus. But in this case, if we divide those two values, we are not getting that equal to Young's modulus. So how is that possible?
No, no. Here, the true strain value might not be equal to the engineering strain value. No? So in the Young's modulus, uh, you actually use that the true strain may not hold true. So that's the point.
Okay. Okay, sir.
So so okay then. If we move to our next question, it says that The flow stress of the material is given. So that's the strain relationship which we already know by now. And then the strain hardening exponent is 0.1. Epsilon is the true strain and K is the strength coefficient. A rod made up of this material has a length of 200 millimeters. A compressive load is applied on the rod to reduce its length by 10 millimeters, and then the load is removed. Okay, so the Young's modulus of elasticity of the material is 250 gigapascals, and the final length is 190.1362 millimeters. Then you have to find the value of K. Okay, so the problem is similar to the earlier question. Only little tweaks may be required. So give it a try, and then you will actually see the solution. So let's look at the solution. The stress strain relationship is given to you with the strain hardening exponent value of 0.1. Length of the material is 200, and then a compressive load is applied here, and the length is reduced by 10. So uh, 200 to 190, and then the load is removed, and then some recovery is there. So the final length becomes 190.1362 mm. Okay. So the Young's modulus is 250. Then you have to find the value of this coefficient K. So very simple. So the rod is compressed by 10 mm. By applying a compressive load, the true strain then is given by because this is in transverse direction. So you have uh, length ln natural log of 190, which is the final length upon the initial length is 200. So that is minus of 0.0513. Okay, and then the stress strain relationship has been given here, which is sigma naught is k epsilon power n, and epsilon we have just found out to be 0.0513, and the exponent is 0.1. Okay, so again, for elastic case, we know that some elastic can be related by Hooke's law as sigma by E. So just compare these two formulations. So we know delta L by L can also give you the strain value. And for elastic case, the Hooke's law, using Hooke's law, sigma by E can also give you the strain value. So by now, you only unknown value here remains to be the K, strength coefficient K. Then if we compare this both LHS and RHS sides, we can find out the value of K.
Sir, one doubt, sir.
Yeah, yeah.
Sir, hypothetically in this question, if we had to find the loss in strain energy, then how would
Hmm.
we go about it?
So you know how to find strain energy.
Strain energy, I think, strain into stress. I think that is the
So
formula.
half of that gives you the average strain energy.
Okay. Okay. So we just like potential energy, we just subtracted
Yeah,
that.
yeah, yeah, yeah.
Got it.
So now we will move ahead to our next question, which says the true stress and true strain diagram is given here. Okay, so the material undergoes plastic deformation. As you can see, there is also non-linear strain hardening here. The material loses some energies and it doesn't come back to your initial position. Okay, so it says there is no loading up to point A. Okay, there is loading up to point A, and then up to stress of 500 megapascals and a strain of 0.5. Okay, so the point if you drop a slope at point A, you can find that the strain is 0.5. Then from point A, there is unloading up to point B, and that corresponds to a stress of 100 megapascals. Now the Young's modulus is given as 200 gigapascal, then the natural strain at point B has to be found out. Okay, so you have to find out the strain at point B. Please give it a try, and then we will see the solution in a while. Okay, so let's see the solution now. Mm, so the problem is with deals with determining the true strain value after the material has recovered to some extent or undergone some elastic recovery, but didn't come back to its initial position. Okay, so you can solve it by simple geometrical concepts. If you simply drop a line from A up to the abscissa, you know the strain at point A is zero point 0.5. Okay? You also know the true stress values corresponding to point A and point B. Now you know that from this line, okay, AC by BC is the slope of this line, right? The path that the material follows while coming back after during unloading process. Okay, the AC by BC is the slope. Again, you know from Hooke's law, Young's modulus is the slope of a stress strain curve, right? So just equating E as AC upon BC, you know AC as the difference between the stress at C and stress at A, and BC remains the unknown. So if you can find BC using that, then you can simply subtract it from the total strain value up to point A to find out the strain value at point B, right? So in this case, so BC becomes 400 upon 200,000, which is equal to 0.002, and you can simply subtract the BC strain value up to point C from B to C from the total strain value, that is zero point 0.5, to find out the strain value at point B. Okay, so please take a note and then we'll proceed to our next question. So moving ahead, one more similar type of question where true stress versus true strain relationship is related by this equation where K value or strength coefficient value is 1020 megapascals and the cross-sectional area at the start of the test is 100 millimeters square. When the stress and strain values are equal to 0, you have to find out the cross-sectional area at the time of necking. So if you are not aware, so necking is the process of beginning of rupture or fracture of the material. So that happens when the ultimate stress point is reached, after which the material starts to fail. That is the necking point in the stress strain curve. So the initial area is given. You have to find the area at the necking point.
Sir, for last question, answer.
Can you see the answer on the screen?
Yeah, sir. Sorry.
So we discussed about the necking process, right? Where the ultimate tensile strength is reached. Now, how do you find uh, what like at necking point? You might be knowing that the true strain becomes equal to strain hardening exponent n. So how do you find that? Just you have to find the maximum stress, which you can find out by differentiating that with true strain and equating it to zero. Okay, and when you do that, you'll find the true strain values coming equal to n at the necking point, right? Just that is the maximization, uh, the mathematical model of finding out the maximized magnitude, right? So at ultimate tensile strength, it is the neck formation starts. Okay, so the epsilon t, then you can equate it to n value 0.4, which is again ln of initial to final area. Okay, so from that you can find out AF to be 67.032 millimeters squares, right? So you can see how much it is reducing from 100 to 67, after beyond which the material starts to fail. All right, so let's look at one question, one conceptual question here. It is about a copper wire which is of same length but double the diameter of a steel wire, right? Both the wires are hung from same roof, are stressed by the same stretching force. Okay, delta LC and delta LS are the elongation values of the copper and steel wires, and gamma C and gamma S are the Young's modulus value of the copper and steel wires. So it is said that gamma C is equal to 5 times of gamma S. Then what will be the elongation ratio of the copper to steel? So for instance, let us actually recapitulate a little about the stress strain curve. So here you have up to this point P being the proportionality limit up to which Hooke's law is maintained, and then you have the elastic limits. In most of the cases, these are too close, and we consider proportionality and elastic limit to be of same magnitude. Okay, and then you have this upper yield point E, and then you have the lower yield point YP. So upper yield point is where the material starts to yield, and because of yielding, the defects starts to move, and because of the movement of the defects, and the stress value suddenly drops with uh, comparing to the strain value, and then you reach to the lower yield point from which the piling up of the defects actually starts to lead to strain hardening process. So because of strain hardening, the material undergoes strengthening process, and the stress magnitude then falls uh, low slowly as compared to the strain. So what we can do is we can load the material higher in this region. So slowly we reach to the necking breaking stress value. It is called as the necking point N, from which the failure starts, and then the material fails at point B, being the breaking point. Okay. And then there is something called permanent set point, when the material has crossed its elastic limit and is in the plastic deformation region, from which the material undergoes some permanent deformations, and this part of strain is called as the permanent set point, right? So these are some of the relations which you are already aware of. Just you can use them to find out this elongation ratio of the copper wire and the steel wire, and then we'll see the solution. Okay, so the length of the copper wire and diameter, if we assume that to be L and D, then the area is simply cross-sectional area is pi d square by 4. Okay, so in case of steel wire, the dia be double be halved, right? So the copper dia is double of steel dia. So in case of steel wire, the D becomes D by 2, and the area then becomes pi d square by 16, right? Now you can simply put in these values to find out the gamma value. Okay, so you have seen how to find out the Young's modulus here, PL by 8LL. So from that you can find out the Young's modulus value for uh, both the wires using the stretching force to be P in both cases, because the P remains constant in both the cases, right? So the P remains same. Now, if you just compare what has been given as gamma C being equal to 5 times of gamma S, from that you can easily find out the elongation ratio of copper and steel wires, which is 0.05. Okay. So if this is clear to you, then we will look at a uh, again one more conceptual question. It says in the typical stress strain curve, the point D and D are far apart. Okay, so what does that mean? Now, now uh, we have got an idea of the stress strain curve, how the material behaves, right? Now, from that you know all these points, the ultimate strain point, the breaking point, okay, the fracture points. Now, it says that the point D, ultimate strain point, and the fracture point E are far apart. Okay, then the material is what? It's a ductile material, because then you have a longer area in which the material is getting plastically deformed before reaching the ultimate point, right? So the material has higher capability of holding load and stretching, so it is more ductile in nature. So you know all these options, all these definitions: ductile, brittle, malleable, and lustrous. So the explanation follows. Point D shows plastic deformation, and point T shows fracture point. If these points are closer, it means the material will fracture easily or soon. Okay, if these are closer, so you have that plastic deformation region smaller, so that will mean that the material will fracture soon. But if these points are far apart, it means the material will not fracture soon, so the material will continue to deform for more time. So it will show the property ductility. So hence in typical stress strain curve, if points D and D are far apart, it means the material is ductile, right? One more such conceptual question. It asks you what point P and Q are, you know very well. So it is the ultimate tensile stress point, and this is the upper yield point. So it asks why there is a drop after that yield point, and what is the reason? The reason is um, actually the flow, the effect of defects and dislocation defects in the material. So we have in the earlier classes, in the earlier initial classes, we have discussed about the dislocation factor, how many types of dislocations can a material encounter, and when these dislocations start flowing, the stress magnitude suddenly drops, and that becomes the reason of a sudden dip in the stress strain curve. Okay, so then again it starts to rise. Okay, so that is because of strain hardening. By now you all know what strain hardening means. So the piling up of those defects gradually hardens or strengthens the material, because the flow of the defects is hindered because of the piling up of one over the other, and then the material strengthens, and the stress actually the material's capability to hold more load actually increases, and because the stress value uh, slowly increases with respect to the strain, right? So that's what happens, and that is why there is a rise. So that is called strain hardening effect. So if that is clear, then we have one final question for today. It asks a strip with a cross section. It is out of rolling process. You can consider a 2 high mil roll. So it says a strip with cross section of 150 cross 6 mm is being rolled, 20% reduction area with 400 mm diameter steel rolls. Before and after rolling, the shear yield stress of the material is 0.35 kilonewton per mm square and 0.4 kilonewton per mm square respectively. You have to calculate the final strip thickness, the average yield stress during the process, and the angle subtended by deformation zone at the roll center, and the location of the neutral point N. You can assume the friction coefficient to a 0.1, right? So one tip is that since in roll process, no widening or the spread is considered to be zero, so the 20% reduction implies a longitudinal strain of 0.2 with consequently 20% reduction in the thickness, right? So therefore, the final strip thickness will be 80% of the initial thickness, okay? 80% of 6 mm. So please try to attempt, and then we'll see the solution. So let us quickly look at the solution to this problem. Um, we had already said how the thickness is 80% because 20% reduction has been mentioned, so it becomes 4.8 millimeters. Now this question is you have to first look and understand the derivation, which I am not going to show now. It will be taught to you in your regular classes. So now let's look at the problem. Now you have been given the yield stress of the material before and after rolling process. So the average yield stress becomes half of the sum of these two, so it becomes 0.375 kilopascals. And then it is clear that at the roll center, the angle subtended at the roll center, it is the difference in the thickness upon the radius, roll radius r, square root of that will give you 10775 radians. Okay. The next point is you have to find out the location of the neutral point n. So first, let me quickly show you what the neutral point is, what happens at the neutral point. So it is the point where the surface velocity of the roll will be equal to the velocity of the work. In other words, if it is a sheet rolling process, the velocity of the sheet movement will be equal to the velocity of the roll, right? So that is called as neutral point or no slip point. The velocity of the workpiece, increases steadily from entrance to exit, and then it decreases. So that is at the neutral point when no slip is there and the velocity becomes equal. Now you have to determine the location of the neutral point, that is theta n. For that, lambda n is a dimensionless constant have to be find out. Okay, so that you can find out using this particular equation, which then again ask you to find the lambda I value. Okay, so lambda I value comes again from this equation, which again depends upon theta value. So theta we have found out earlier, the angle subtended at the center. So using that, you can find lambda I. You can again put back lambda I here to find out lambda n. Once you have found out lambda n, you can just use this equation to find out the value of theta n, right? So in that way, so lambda I value becomes 5.99. You can just practice and check if these are right back home. And then lambda n becomes 1.88. So theta n can be expressed as this equation. Simply, then you can find out the theta n value to a point 023 radians. So then you have to again as a continuation to this problem, we are actually trying to find out the roll separating force F. Okay, so for that we use that integration rule. You must be aware about Simpson's rule for 4 and 8 divisions after and before the location of the neutral point. Now this is the procedure which is followed. So you can simply find out the theta value after the neutral point as dividing that by 4. So it is coming out to 0.00575, the magnitude of each particular divisions. And then before the neutral point, if you follow the same process, you can find out the magnitude of one division to be 0.00681. Okay. So from using these values, you can find out 5 values for the before data and there or sorry after data, and then subsequently for the before data. So there from theta you can find out the y value if you know the rolling process. So the thickness of the sheet is given by y. So for that you can find out the y value, and then using that y value you can find out the lambda, and hence the stress, the force value, the roll force value for that particular point. Okay, so that way you can, because we have certain number of divisions, so for that we can have a certain number of p values, and then we can simply use the Simpson's rule. So you can revisit the Simpson's concept from where r is the roll radius here. R d theta is the area. Okay, r is the radius and theta is the angle subtended. So r d theta is the area. And for the after part and the before part, you can separately integrate, and using the Simpson's rule, you can use the numerical integration technique to find out the total roll force. Okay? 12.73 kilonewton per mm. Again, for two rolls, you have to multiply that, and then for the total width, you can multiply the width of the strip as 150 mm to find out to be 1909 kilonewtons. Right. So the driving torque is simply r square mu d theta. R d theta is your area, and mu r is your force. So that is the total torque value and multiplied with force value. So for the left, for the before and after rolling process, you again find out the division subtraction to find out the total torque to be around 100 kilonewtons. Okay, and then you can simply multiply it with the total width of the strip to find out the this is a torque per width per unit width, and for the total width, the total torque becomes almost equal to 15 kilonewton meter. Okay. Now, the total power, you can multiply the angular velocity of the rolls, omega, and that will give you the total power in radians per second. Omega is in radians per second, so the total power is in kilowatts. Okay, so omega, the RPM is given in the question, right? So from that, you can find out omega to be 2.5 radian per second, and the total power then becomes twice for two rolls, it is 95.6 kilowatts. So here we'll conclude today's session, and we will actually meet again for the next session. You can try and solve this kind of rolling problems. This will be enough to actually help you solve any kind of questions out of rolling. So these slides will be shared to you, practice back home, and then it won't be difficult to solve the current week's assignment questions, I suppose.